Alright, now this is another next level of things getting harder. Inclines and pulleys. And we're going to start here with inclines because this is the required topic, especially at the Regents level. And so when you have an object on a raised surface at an angle, this is what we call an inclined plane. And so when you have this box here, this object, resting on an incline, its weight will still be going vertically downward, but it will have two different components now. This weight will have a component that's perpendicular to the incline, and you're going to have another one that goes parallel to the incline. And when given the angle of the incline, you could calculate for these components. Alright, so thinking back that the weight is still equal to m times g, you can get that FG parallel, the one parallel to the incline, is equal to FG sine theta, or simply mg sine theta, depending on what you're given. The same thing applies to the perpendicular component, FG cosine theta or mg cosine theta. Okay, and a good phrase to remember to help tell the difference between these two, because these equations are not on the reference table. And I gotta give credit to Mr. Garger for teaching me this phrase. Sine goes down the incline. So going down the incline, you're taking the parallel component. Alright, and then that'll help you remember that cosine is the other component, the perpendicular component. And here, you can easily see that because we're on an incline, the surface is tilted. So will the normal force coming out of the surface. So in response to the perpendicular weight pushing down on the surface, you're going to have the normal force now be opposite that component. So when you're on inclines, the normal force will equal this, the weight perpendicular to the plane. Now friction will act along the parallel plane. It could either act with the weight going down, or it could act against the weight going up, because it depends on the direction of motion. So remember that friction opposes the direction of motion. If the object going up, friction will go down. If you have the object sliding down the incline, then it'll go up. So the force of friction will act in the same plane as FG parallel, but it doesn't necessarily have to oppose it. Oops, that's not FG, it's supposed to be FF. There we go. So force of friction can act upward against the sliding down, or it can act going downward friction, going against the motion going up the incline if you have something pushing it up. Okay? And then here we talk about pulleys. So this is more common at the AP level, but I think I wanted to teach this anyway because this is a good introduction to two body systems. So that means we're dealing with two different masses, but even when you have multiple masses, they still comprise the same system. And when you have a system of masses, they share the same net force and the same acceleration. And we start with this pulley system with two hanging masses hanging vertically. So that means the force of gravity acting on both of these will act as such. They still act downward, and because they're both connected by string, the tension force will act opposite their weight. In this type of a system, the system will accelerate towards the side with the greater mass. So if M1 is bigger, it'll go down M1 side. If M2 is bigger, then the system will go down M2 side. But if one goes down, the other mass will go up. Alright? So in this system, your net force will be comprised of both weights and the canceling out of the tension forces. So in our case here, we're going to say that M1 is smaller than M2, so M2 is the bigger one. That means we're going to accelerate down M2 side. So I usually like to start with that as our leading force. That's the one that drives the motion. The weight of M2 being bigger, it accelerates the system down that side. And that tension force opposite Fg2, well, we're going to subtract that because it opposes the motion. The tension on the other side goes along with the motion because it's helping to pull the other object up. And then we have the weight of the other object, Fg1, opposing the direction of motion. So hence why these two are being subtracted, the weights are being subtracted from each other. And so really, the net force is really a combination of both weights of the object acting opposite each other. So imagine you took these two masses, remove them from the pulley, and lay them side by side horizontally on a surface, kind of like this. So essentially, these two weights pulling in opposite directions will eventually account for the net force and cause an acceleration in the system. All right. So the mass of the system and the acceleration, they're all shared together. And remember that the mass of the system is a combination of both masses together. So if you ever want to figure out the acceleration of the system, this is how you would do it. Okay? That special fun equation. So if you had numbers to these, all you need to do is plug those numbers into this equation, and voila, you can figure out the acceleration of the system. And then we have this special case. You have one hanging vertically and the other one resting on a table. So if in the case that you have an acceleration happening, that means M1 is pulling everything downward, and then M2 is following along in the direction pulling forward. But in the case where it's at rest, then you have friction to counteract the weight of the hanging mass. So as usual, this will have a weight pulling down, and in response, this will have tension pulling up. The other block will have tension pulling it forward to the right, but it will also sometimes, depending on the surface, will have friction acting opposite that. So in the case where the system is in equilibrium, so if in equilibrium, then we have the weight of the hanging mass equaling the force of friction. So these two balance each other out, keeping the system stabilized at rest and equilibrium. And so once you make that conclusion, you're able to solve other things such as coefficient of friction, etc., and other things about the system. All right? And so let me also make a note here. If not in equilibrium, then Fg1 drives the acceleration.